Good afternoon, everyone. My report today is about the physical properties of aldehydes and ketones. Aldehydes and ketones are simple compounds which contain a carbonyl group, a carbon-oxygen double bond. They are simple in the sense that they don't have other reactive groups like OH or Cl attached directly to the carbon atom in the carbonyl group, as you might find for example in carboxylic acids containing COOH. Aldehydes. In aldehydes, the carbonyl group has a hydrogen atom attached to it together with either a second hydrogen atom or more commonly a hydrocarbon group which might be an alkyl group or one containing a benzene ring. Here are some examples of aldehydes. Notice that these all have exactly the same end to the molecule. All that differs is the complexity of the other group attached. When you are writing formula for this, the aldehyde group, the carbonyl group with the hydrogen atom attached, is always written as CHO and never as COH. Because if you will write it as COH, it can be easily mistaken or confused with an alcohol. Ethanol, for example, is written as CH3CHO and methanol as HCHO. Ketones. In ketones, the carbonyl group has two hydrocarbon groups attached. Again, these can be either alkyl groups or ones containing benzene rings, just like the aldehydes. We'll concentrate on those containing alkyl groups just to keep things simple. Here are some examples of ketones. Notice that ketones never have a hydrogen atom attached to the carbonyl group. Propanone is normally written as CH3COCH3. Where does aldehydes and ketones differ? An aldehyde differs from a ketone by having a hydrogen atom attached to the carbonyl group. This makes the aldehydes very easy to oxidize. For example, ethanol, CH3CHO, is very easily oxidized to either ethanoic acid or ethanoate ions. While ketones, on the other hand, don't have that hydrogen atom just like the aldehydes. And ketones are resistant to oxidation. They are only oxidized by powerful oxidizing agents which have the ability to break carbon-to-carbon bonds. In summary, aldehyde has hydrogen atom attached to the carbonyl group, and it is very easy to oxidize. While ketones don't have hydrogen atom and they are resistant to oxidation. They only oxidize when you will use a very strong or powerful oxidizing agent. The physical state and smell of aldehydes and ketones. The lower aldehydes have sharp, pungent odor, while the lower ketones have pleasant smelling liquids, while higher ones are solids. Methanol, HCHO, is a gas at room temperature and its 40% aqueous solution is known as formalin. Ethanol, CH3CHO, is a volatile liquid. Other aldehydes and ketones are liquid or solid at room temperature. An example of aldehyde is formaldehyde. Formaldehyde is a gas that is dissolved in water to form the compound formalin, and formalin are used to embalm dead bodies. The most common ketone is acetone, which is an excellent solvent for a number of plastics and synthetic fibers. Now let's talk about the boiling points of aldehydes and ketones. Methanol is a gas that has a boiling point of negative 21 degrees Celsius and ethanol has a boiling point of positive 21 degrees Celsius. That means that ethanol boils at close to room temperature. The other aldehydes and the ketones are liquids. with boiling points rising as the molecules get bigger. The size of the boiling point is governed by the strength of the intermolecular forces. These intermolecular forces are the van der Waals dispersion forces. These attractions get stronger as the molecules get longer and have more electrons. That increases the size of the temporary dipoles that are set up. This is why the boiling points increases as the number of carbon atoms in the chains increases, irrespective of whether you are talking about aldehydes or ketones. Here in the table, we can see that the higher the number of carbons, or also the higher the boiling point. Another intermolecular forces is the van der Waals dipole-to-dipole attraction. Both aldehydes and ketones are polar molecules because of the presence of the carbon-oxygen double bond, as well as the dispersion forces. There will also be attractions between the permanent dipoles on nearby molecules. That means that the boiling points will be higher than those of similarly sized hydrocarbons which only have dispersion forces. Here are some examples of three similarly sized molecules: the alkane, aldehyde, and alcohol. They have similar lengths and similar number of electrons, although not identical. Notice that the aldehyde with dipole-to-dipole attractions as well as dispersion forces has a higher boiling point of positive 21 degrees Celsius, higher than the similarly sized alkane, which only has dispersion forces and has a negative 42 degrees Celsius boiling point. However, the aldehyde's boiling point isn't as high as the alcohol's. In the alcohol, there is hydrogen bonding as well as the other two kinds of intermolecular attractions. That's why alcohol's boiling point is higher than aldehyde and alkane, even though they have similar lengths and similar number of electrons. So alkane has the lowest boiling point because it only has dispersion forces, while aldehyde is higher than alkane because it has dispersion forces as well as dipole-to-dipole attraction. And lastly, alcohol has the highest boiling point among the three examples because it has dispersion forces, dipole-to-dipole attraction, and hydrogen bonding. Now, let's talk about the solubility in water of aldehydes and ketones. The small aldehydes and ketones are freely soluble in water, but solubility falls with chain lengths. For example, methanol, ethanol, and propanone, the common small aldehydes and ketones, are miscible in water in all proportion. The reason for the solubility is that although aldehydes and ketones can't hydrogen bond with themselves because they are highly polar molecules and they don't have any hydrogen atoms attached directly to the oxygen, they can still hydrogen bond with water molecules. Here in the table, we can see that the number of carbons can affect the solubility of aldehydes and ketones. Here we can see that methanol, which has only one carbon, is miscible in water. Also ethanol because it has only two carbons. While in propanol, it has 3 carbons. It is slightly soluble in water. And butanol has 4 carbons. It is very slightly soluble. While pentanol and hexanol, they have 5 and 6 carbons. They are insoluble in water because the number of carbons are higher. Just like aldehydes, the number of carbons of ketones also affect its solubility in water. One of the slightly positive hydrogen atoms in a water molecule can be sufficiently attracted to one of the lone pairs on the oxygen atom of an aldehyde or ketone for a hydrogen bond to be formed. There will also, of course, be dispersion forces and dipole-to-dipole attractions between the aldehyde or ketone and the water molecule. Forming these attractions releases energy which helps to supply the energy needed to separate the water molecules and aldehyde or ketone molecules from each other before they can mix together. As chain length increases or the number of carbons increases, the hydrocarbon tails of the molecules start to get in the way. By forcing themselves between water molecules, they break the relatively strong hydrogen bonds between water molecules without replacing them by anything as good. That's why if the number of carbons is higher, they can't be soluble in water, just like in the table shown earlier. This makes the process energetically less profitable and so solubility decreases. That's all for my report. Thank you for listening.